Hello everyone. We finally reached the last chapter of this semester, which is simple linear regression. In this chapter, we basically discussed how to find the relationship between two variables, and we assume that their relationship is a simple linear relationship. So first, in this chapter we discussed what is deterministic model and what is probabilistic model. And if you take a look at the general formula for a probabilistic model, it incorporates a deterministic component and a random error. And always remember the average value for a probabilistic model always equal to the deterministic model, because here you are uh, calculating an average, and the random error part is impossible to determine. So the average value for the probabilistic model is equal to its deterministic component. And as I said before, we assume the relationship between these two variables is a simple linear relationship. So therefore, we assume they have such a relationship. If we plot this function in a coordinate, it is just a straight line. The beta 0 here represent the y-intercept, and beta 1 represent the slope. And like I said before, the average value of a probabilistic model always equal to its deterministic part. So therefore, if we take a look at this formula here, that the expected value of y always equal to beta 0 plus beta 1 multiplied by x. The epsilon here is the random error, is the random part. We cannot predict it. And please pay attention, if you are using this model, we have to take the range of x into consideration. So now, as I said, we are going to find the relationship between these two variables. And we have a sample of this variable. So basically, we are using this sample to calculate a relationship, to calculate a formula. And that formula is the estimate for the relationship of the whole population. So basically, we have x and y two variables. Of course, there's a population of x and population of y. However, very similar to a lot of questions we have discussed before, it is impossible for us to get the population. Therefore, we'll just get a sample of x and a sample of y. And we use this sample to make inference of the relationship in the population. So how do we utilize this sample to calculate the relationship? We employ some method called the least square estimate. I won't go into detail about the reasoning behind this method, but basically, the the main rationale behind this method is that we want to make the random part of this function as small as possible. So that's why we are calculating this SSE, which is the sum of the square of the random error. And we are trying to make the SSE here as small as possible. So if you're interested, you can definitely get the derivative of this function and calculate when the function will reach its minimum value. However, we'll skip that part since that is not what we are learning here in this class, and that process is not important for the final result we will get. So if we employ this method, we'll have a beta 1 hat equal to this, and beta 0 hat equal to this. So please pay attention. They have this little hat on beta 1 and beta 0, which means that they are sample statistics. They are not population statistics. Somewhere out there, there is a true beta 1 and there is a true beta 0 for the whole population. However, since we don't have the population, we only have a sample. We don't know the true value of beta 1 and beta 0. Therefore, we can only calculate beta 1 hat and beta 0 hat based on the sample we get. And we use this two values to estimate the true beta 1 and true beta 0. And you can see SSXY and SSXS. This is how you calculate and remember these three formula. By the way, this chapter you have a lot of new notations and new formula, but they basically evolve around these three formulas here. So just pay attention to this and don't mix them together. Always know which formula you're using and which value you're calculating. So therefore, since we have the beta 1 hat and beta 0 hat, we can get the line, which is called the least square line. And please pay attention. As we said here, in the model, we incorporate the absolute. But in the line, we didn't incorporate the absolute. There's no absolute here. It is because this line, as we have the sample here, this line is something, this is the deterministic component we want to express. And we definitely don't want to incorporate the random part in it because we don't know about the random part, so we cannot incorporate the random part. And also, when we are getting the y value, we are getting also has a hat in here. It means that it is an estimate. It is not the true value. If we want to get the true value, however, we will definitely incorporate the random part because the true value has the random part. But we want to have an estimate of the true value, then we don't incorporate the random part. And there are some properties of the least square line you need to know. First is that the SSE of this line is smaller than any other line. This is how we get the function of a line. We find the minimum value of SSE. And the second property is the SSE is equal to 0. Pay attention that the SSE is equal to the sum of the square random error. So it's always bigger or equal than 0. And moreover, SSE equal to 0, it does not mean that the sum of all the random error equal to 0. The sum of all the random error is still bigger than 0. Maybe bigger than 0, maybe smaller than 0. But it does not mean the sum of all the random error is equal to 0. And the third property you need to know that this line always passes through the point x mean and y mean. And when calculating this line, we have some assumptions about this model. The first assumption is that the mean of the probability distribution of epsilon is 0. And that is also why we don't incorporate epsilon here, because the expected value, the mean of epsilon is 0. That's our assumption, so we just don't incorporate here. If your assumption is the mean of the random error is 1 or 10, then you have to say plus 1 here or plus 10 here. But On the other hand, it is very irrational to say some random error, the mean of some random error is 10 or 1. So therefore, it's reasonable for us to make this assumption. The mean is 0. The second assumption is that the variance of epsilon is constant. The third assumption is we assume epsilon follows a normal distribution. The last assumption is that the value of epsilon associated with any two observed value of y are independent. So if I have a y of 1 and I have another y of 10, the epsilon related to these two values, they have no connections. Since we mentioned the variance of epsilon, we'll see how to calculate. And this is the formula of how to calculate the variance. Again, here we are using S. The sigma represents the population variance, population standard deviation. S represents the sample standard deviation. Since we only have sample, not population, we are using the sample standard deviation tool to estimate the population variance. This is how we calculate SSE, and pay attention, there's a special relationship between SSE and beta 1 half. So for the following part of this chapter, it just involves hypothesis test and confidence interval. As we have talked a lot about hypothesis test and confidence interval. If you remember what I said in the last chapter, inference based on two samples, I said that whenever you are dealing with hypothesis test or confidence interval, it doesn't matter it is one sample or two sample, it is Z stats or T stats, or you are dealing with population mean or probably sample proportion or sample mean. You have to find the correct standard deviation to calculate Z-score or T-score, because in different scenarios you have different standard deviation, you have different S or different sigma. So therefore, you have to find the right S to apply into a formula. And for our simple linear regression, we will treat the S we calculated here as you can think of it as the population, you can think of it as the population standard deviation. You may say, well, I just said it is a sample thing. It is a sample statistic, not a population statistic. What I want you to relate to is that if you remember in the sample distribution chapter, we said the population has a variance, and the sampling distribution of sample mean also has its own variance. And the variance of sampling distribution of sample mean is smaller than the population variance. It is population variance divided by n, divided by the divided by the sample size. So therefore, when we are trying to say do a hypothesis test or confidence interval in this simple linear regression chapter, you can treat the S here as the ultimate standard deviation, and you will alter it based on different scenarios. you are calculating. For example, you can see it directly here. If you are doing a hypothesis test on beta 1, you need to adjust this as according to this form, right? And you may also need to adjust it in a different way in the following part. What I want you to remember from all this I said is that treat this as the only standard deviation we have, the biggest standard deviation we have. And then let's move on to hypothesis test on beta 1. We basically want to know whether the slope of this line is equal to 0 or not. You can see the non-hypothesis is that beta 1 equal to 0. It is a two-tailed test. We just want to know is there a relationship or not, right? And this is the like I said before, this is the standard deviation of beta 1 hat. Like, treat beta 1 hat as a random variable. It is a random variable, and this is the standard deviation of its distribution. And it's a t-stats. You need to calculate a t-score. This is how you do confidence interval. And since it's a t-score, always pay attention to the degree of freedom. And then we have coefficient of correlation. This is how you calculate it. Pay attention, its value always is between -1 and 1. This value expresses how strong is this linear relationship. With 1 means very strong. -1 also means very strong, but in a negative way. However, if you're calculating some sample with an r equal to 0, it does not mean that this sample don't have relationship between the two variables. Maybe they just don't have a linear relationship. In this chapter, we only deal with linear relationship. Next one, we have coefficient of determination. Coefficient of determination represents the proportion of total sample around the x bar that is explained by the linear relationship. So using the formula, you calculate how many sample you can explain, right? So coefficient of determination basically equal to the square of x, to the square of r. This is how you calculate it. Here, this line, just a little variation, but it's make the matter more complicated. We are introducing a lot of new notations. Just don't get confused. The relation between these notations are very simple, but don't get confused. You're gonna call S as YY as SST, and you're gonna call this as SSR, and we have introduced the SSE. This is the minimum value we want to find, and they have such a relationship. You can use such a relationship to calculate the square of r. Finally, last part of this chapter is about estimate and predict. It involves the discussion about epsilon. If you remember, let's just say we have a new x value, and we want to find the correspondent y. And there are two types of correspondent y we can get from this x value. The first one is the mean value of the y, which means the estimated value of y, the expected value of y. It is only concerned about the deterministic part of the model. However, if you want to estimate a new individual y, a true y, based on a new x, it involves not only the deterministic component of the model, it also involves the random error part of this model, because you are calculating an individual y. So in these two scenarios, you have two different sigmas. This is how you calculate the confidence interval. But pay attention, you have the same point estimate, because no matter what y you are estimating, you only have this line. You can only estimate that point based on the line you calculate. So the point estimator is the same. What is different is the sigma. Always pay attention to the degree of freedom here. And you can get a sense from this graph. The red dot, the red line, represent the expected value of y. And the green line represent any individual value of y. So basically, if I have an x value here, this is the point. The point here is what I can predict from the line I calculate. And this range represent in 95% of all the possible scenarios. The expected value of y will lie within this range. And this range represents, for 95% of all the scenarios, this is the individual y. This is the range for individual y. Relating back to what I said before, the reason why we will get these two range, and the reason why we even have a range, is because we are using a sample to predict the population. The smaller range represent we're using the sample to predict a population mean. And the bigger range represent we are using a sample to predict a sample point in the population. That's why it has a bigger range. And this is all I want to say about this chapter. So this chapter has a lot of new notations in formulas and many complicated formulas. Just don't confuse these formulas and use the correct formula when you are dealing with different scenarios. That's all I want to say. Thank you, everyone.